Hello, welcome back. So, Geography 201, this is Chapter 4, we're on Part 3. So, we left off with the systems of high and low pressure that work on a global fashion. So, remember at the equator, the ITCZ is a global low, and then 30 degrees north and south, you have the subtropical high. Okay? So, moving northward, we have the subpolar low and the polar high. And these work kind of together in a way as well. So it kind of goes backwards. We'll start with the polar high. So at the poles, the north and south pole, right, air is very, very cold. So cold air is dense, right? So dense air, right, at the low. And that's basically 60 degrees north. I'm sorry, dense air is high pressure. Get that backwards all the time myself. So the polar high, cold air, is very, very dense. And then surrounding that at about 60 degrees is the subpolar low, which is about of low pressure. Okay, and this kind of circles the pole. And the subpolar low is a little bit north of us, so you'd say maybe Canada. But this area has a lot of cyclonic systems that bring a lot of storms and a lot of snow. So it's always best, I think, to kind of show these images. This is the whole process. We have basically four main processes, right? The ITCZ here at the equator, right? So the air, it's rising right here, low pressure because it's going up and away, and it leaves all its moisture right here at the equator. Now this air kind of moves north or south, and then at 30 degrees south or north, it comes back down to the surface. So it's dry because it's already lost all its moisture here in the tropics. So it comes down, it's dry, and as it comes back down from the upper atmosphere, it gets compressed, so it's dry and hot. And that's why you have this, what's called the subtropical high pressure system right here. And this tends to also be where most major world deserts form. Now here's the last two, the subpolar hot low and the polar high. So over the poles, right, you have very, very cold, bitterly cold, very dense, high pressure air. And basically, because it just kind of flows away from that, high pressure expands, right? It meets this subpolar low, which is low pressure air right here. So you have that convergence again, okay? Now, those patterns kind of work to set up the next thing. The global pressure patterns work to set up the global surface wind patterns. So generally speaking, on any part of the Earth, the winds at the surface fall into one of these five basic categories. We're going to go through these. Let's start here with the trade winds. Now these are winds that are generally easterly, which means they blow from the east to the west. And it's right near the equator. So between the ITCZ and the subtropical high. Okay? These winds blow basically around the Earth, right near the equator, at between 0 and 30 degrees from the east. So they're blowing this way consistently. And so that covers one of the largest parts of the world's surface. Because they blow so strong and consistently to the east, they're called the trade winds because back in the days of sailing ships, sailors knew this, and they would sail south to between 0 and 30 if they wanted to go east, and just basically hitch a ride on those winds because they were constant. Okay? The Hadley cell, I'm not going to go too much into. I just want you to know that that exists. And these are trade winds at the equator in a loop. Now, right at the equator, the very the ITCZ itself is a little narrow band called the Doldrums. And here there is no surface wind blowing east, west, north, south, because this is where, remember, the ITCZ, the air is kind of being pushed up. So air is flowing vertically, not horizontally. So if you were in a sailing ship back then and you were right at the equator, you had this area of calm, no wind, and your ship would stop. And you were stuck in the doldrums. And that's what that means. Now, the Horse Latitudes, very similar. These, except, are at 30 degrees north and south. So at the equator, you have the doldrums. Between the equator and 30 degrees, you have the Easterlies. And then at 30 degrees, that little band right there, you have the Horse Latitudes. And again, low wind because the movement of the air is vertical, not horizontal. This is where the air is coming down to form the subtropical high. Okay? And so it's dry air, very little wind. Moving north, you have the Westerlies. And this is the winds that we are in. We are in the area that we're covered by the westerlies. And again, surface winds are basically going to the west. And then you have, at the very top, the polar easterlies, which means that at the poles, the winds come from the east. So let's put it all together. And here again is our patterns. So here we have the ITCZ, right, the equator. Right, the air is moving vertically, not horizontally. So right here, very little wind movement north, south, east, west. But between 30 degrees and 0, you have easterly winds. The winds all blow generally this direction. So if you were sailing from, say, Mexico to Asia, you would just literally just hop a ride and just sail these straight across. Columbus used this to sail from Europe to America. He actually sailed down to the Canary Islands and just sailed straight way in there. Now, right here at 30 degrees north and 30 degrees south, you have another area of low surface wind because the air is just moving down. And that's the Horse Latitudes. Then continuing north or south, the winds now blow west. So all of our winds generally in North America come from the west. So if you ever watch the news forecast and they're talking about a winter storm that's coming in from Seattle and then it's going across the plains and the mountains and then Minnesota hits us, that is generally speaking the winds. And then at the very, very top, you have the polar easterlies. So because of the rotation of the Earth, the winds just kind of, the wind, the air at the poles very cold and dense, kind of just basically spreads out, and they go easterly. Okay? So the next level of this model are the upper level winds. So far we've talked about air pressure. We've talked about air pressure patterns. We've talked about surface winds. But now we're going to talk about upper level winds, because remember I said that wind that blows across the surface, it gets slowed down by the surface, like friction, like the buildings and the rocks and the mountains and the trees. But when you get up miles into the atmosphere, right, the wind has nothing to stop it. So what happens is the upper level winds, you'll hear terms like the jet stream. This is winds that blow super fast because there's nothing to stop it. So because they flow so fast, the Coriolis effect makes them curve even more. Okay? And so they flow almost parallel to isobars. I'd said earlier that a wind will never flow parallel. It'll always be perpendicular to an isobar. These come pretty close. Okay? So a great example is the polar jet stream. And so this right here is basically a band of wind between the polar easterlies and the westerlies that we have. And the wind speed up here, and we're talking maybe between 2 to 3 miles on up, can be almost 250 miles. It is so strong that sometimes aircraft will hitch a ride, because if you're going the direction of the jet stream and you're an airplane and you get into it, it's almost like a current river. It makes you go faster, and if you have to fly against it, you actually use more energy. So on this map, the darker the red, the faster the winds. This is the polar jet stream. So it's blowing from west to east, like this. Right? So here's the polar easterlies, here's the westerlies, and this blows in between them up in the higher atmosphere. And because it is blowing so fast, it has these big, huge curves like waves. These are actually called Rossby waves because they are such a deep, deep wave. But what's interesting is that this polar jet stream kind of acts as a boundary. It helps keep the very cold air from the pole here. And so air on this side of the jet stream is generally very, very cold. And air on this side is generally much warmer. Okay? So a couple things about the jet streams. Those Rossby waves kind of undulate like that, almost like a river. There's usually 3 and 6. And they move heat and they move cold. So here's an example. Right here you have the subtropical jet stream, but the more famous one, the polar. So the air here is very, very cold, and here is kind of fair. So this is moving this way. If there's a big ridge this way, it's going to pull heat up from the equator. So sometimes we'll have a day in the winter where it's really, really cold. Remember the polar vortex we had? Here's an example of that. This is a normal pattern. But sometimes we get a big, big, big Rossby wave, and it dips way down. And this dip allows air from the pole to come much, much further south. So I think it was 2 winters ago we had a day where the high, and it was in January, the high temperature for the day was minus 11 degrees Fahrenheit, right? That was one of these events. So air from the North Pole basically came all the way down far south, I believe it was New Mexico in some parts. So it moves cold air. But what was interesting about that was the next day, as this wave moved this way, and then the warm came in, it went from being negative 11 to being 35 degrees above in 2 days. And so that happens. Odd little interesting trivia fact, or kind of a weird thing. Global warming is going to make this happen more often. It's going to give us cold outbreaks more often. And that doesn't make sense at the top of it. Why would global warming make our winters colder? Well, one of the things that makes this a really strong wind is the big amount of difference in temperature between the cold and the warm air. Because remember, difference in temperature can cause difference in pressure, and the greater the difference in pressure, the greater the wind speed. So right now, this is much colder air than here. It's a big difference. It drives this really, really fast wind. But if this wind begins to slow a little bit, it allows these loops to form, almost like a drop, which brings those polar vortexes. As the North Pole and the South Pole get warmer, and they're warming at twice the rate of the rest of the world with global warming, this air isn't as cold as it used to be. So right now, there's not as big of a difference between the air here and here, and these polar jet streams are beginning to slow a little bit, which allows more outbreaks actually of cold air, ironically. All right, we're going to pause right here, and then we're going to finish up with our talk about global and pressure zones.